So I had the extreme good fortune for the bulk of my career at Branch Oceanographic to be able to do exploration in the Bahamas over a period of about 20 years. And part of that had to do with the fact that I was involved in a marine natural products drug discovery program. So we did I guess the politically incorrect term, bioprospecting or biodiscovery of the Bahamian deepwater, shallow water and deepwater communities over a period of about 20 years. And I will say it was the high point of my scientific career to be able to explore some of these deepwater habitats that Professor Eberle just described in his previous talk. Let me get this down. Okay, so I'm just going to give you a quick overview about marine natural products drug discovery and why look to the oceans. Incredible source of biodiversity. That biological diversity translates into chemical diversity, and that chemical diversity translates into potential for discovery of new drugs. A lot of the drugs that we use today are based on natural products from terrestrial sources and from microorganisms. Over the past 4 decades, about 40,000 chemicals derived from marine organisms have been discovered, and many of these have pharmaceutical relevance. These are not compounds that have been developed into drugs, but have some kind of pharmaceutical relevance. And you can see here a list of the organisms from which most of these compounds have been isolated, but by far the largest source, the greatest source of chemicals with potential pharmaceutical relevance has been from sponges, and that's my area of expertise as well. It's the reason why I came and joined that program at Harbor Branch back in 1984 when I was 5 years old. So the sponges are dominant components of most benthic marine ecosystems. More than actually 8,500 described species. I would say in the Bahamas, I'm going to be conservative, and I would say that we have at least 600 species of sponges in the Bahamas, and that's a very conservative estimate. So the process by which we discover drugs from deepwater environments is we go out and collect samples, and we test them for activity against disease processes. And so we were very fortunate to have available to us not only the ability to go scuba diving, but also we had ships and submersibles, the Johnson Sea-Link submersibles that Gregor Eberle talked about. And we were able to do collections and very precise sampling from deepwater environments, again, over a period of about 20 years. And so our strategy was really to focus on diversity. So the diversity of sponges, and again, because we have hundreds and hundreds of species of sponges, soft corals. We never really collected stony corals for a variety of reasons, but focusing on gorgonians and tunicates and sponges. And our focus was on collecting larger organisms. So, and that's why I think our estimates for biodiversity are really, really low, because we weren't looking at cryptic things. We were looking at things that were kind of fist-sized or greater, so that we could isolate chemicals that could be tested for pharmaceutical relevance. And we were the Johnson Sea-Link submersible had very nice manipulator arm that would allow us to collect things using a claw or a scoop or a suction device. And over this 20-year period, the places on that map that are red dots are areas where we made collections mostly by submersible, but it also includes collections that we made at depths, deep scuba, 50 meters or deeper. So we made a few dives at 50 meters, but scuba dives, but mostly submersible operations. Over that 20-year period, we made about 1,000 dives. So really, really incredible opportunity to survey these areas and to do some collections. And I especially want to thank the government of the Bahamas for making it so easy for us to work here. I mean, I've had to arrange for expeditions all over the world, and I will tell you that by far the easiest, most collaborative, most cooperative place to work, and really the loveliest place to work, has been in the Bahamas. And I especially want to thank people with whom we worked back during that period of time, Colin Higgs and Michael Brain and Valier Delavio, for their help in expediting, facilitating the permitting process. It was always done under full disclosure. the government knew that what we were doing was collecting samples for drug discovery research. And we have some agreements in place, should any of these ever make it commercially, that some compensation would go back to the Bahamas as well. Okay, so what do we do once we get a sample? We make what we call an extract. So when you have a cup of coffee in the morning, the active ingredient in that coffee is caffeine. We're looking for the caffeine in these sponges. We're looking for the compound, the single compound that's responsible for the activity that we might be observing, whether that activity is anti-cancer activity or antimicrobial activity. We work with a number of collaborators in the biotech industry and in pharma and other universities, looking at infectious diseases, things like malaria, looking at neurodegenerative disorders as well. So it's a broad variety of pharmaceutical applications that we're working on. And once we find something, we need to figure out how it does what it does. And so these are photomicrographs of cancer cells that were treated with a compound that we isolated from a sponge we first collected here in the Bahamas. The sponge is called Discodermia. The compound was called discodermalide, and it actually made it into clinical trials. The way it worked was to prevent the cells from dividing and to cause that microtubule network in our cells to kind of stick together so the cells couldn't divide. But if you want to develop one of these compounds, you have to patent it, basically. You have to patent the compound, and you have to be able to describe how that compound does what it does. Only then will a pharmaceutical company decide that it's worth it for them to continue on with preclinical and clinical trials. So what have we found so far? And this is just focusing on samples of sponges from the Bahamas. I mentioned discodermalide. We first collected this off of Freeport, actually doing a deep dive, scuba dive, and then after that did most of the collections, again, off of the Freeport-Lucaya area using our submersible at about 450 feet. Another compound a series of compounds called the top sentence that are very potent anti-inflammatory compounds come from a sponge called Spongoceroides, again, very common sponge in deep water environments. A related sponge to Spongoceroides, this rather, I don't know, they're not really pretty sponges, but you gotta love them anyway. And there was another series of compounds that have activity against malaria, so we're working on those as well. Liodromatolide comes from a very interesting sponge that's a rock-like sponge called lithistids, these groups of sponges that are very rock-like. The Bahamas has an incredible diversity of lithistid sponges. And this sponge is also a very potent anti-tumor agent. Another sponge called Batzella that we collected off of Bimini in 420 feet has another anti-cancer compound. Now, we do more than just drug discovery with these samples. We prepare a variety of subsamples. We prepare taxonomic vouchers in ethanol, and we have a museum, an archival museum at Harbor Branch from which samples can be borrowed and studied. So we have a huge collection of samples from the Bahamas and really from other places that we've done our collections as well. Each sample is frozen for chemistry at minus 20 degrees C. And as a result of just these two types of preservation, these samples have now been made available to do molecular work. So looking at connectivity of samples, looking at genetics, looking at their molecular identification as well. Since 2005, we also started doing what we called a molecular arc. So we flash froze samples at minus 80 degrees, and we also had them in RNA later. So it makes them even more valuable for molecular work. And of course, every sample was extracted in ethanol for our bioassays. And some of these were also frozen at minus 80. Actually, all of the deep water samples were frozen at minus 80 degrees in glycerol for subsequent work on microbial communities. And so we're becoming more and more interested in the holobiome, what exists in the sponges and the corals, for example, the microbial community. So these samples are available for that type of work as well. And then we have photos that we've taken of each of these samples, both in situ, in most cases in situ photographs and deck photographs as well. And so how do we keep track of all of these? Well, we have a database for every sample that we've collected, and we assign a unique identifier that we can sort on. We have sample images that are in that access database as well. And as I mentioned, we have vouchers and frozen samples, and they're all tracked. So we have a very, very, very good tracking system. So at any point in time, if somebody comes to me and say, hey, what did we collect in Bimini in 1987, we can go in and search on that. I can tell you how many samples we have, what types of vouchers we have, if we have frozen samples as well. It's a resource that's available to be used. So this is just a screenshot of our database, so we can enter data on, and we collect the data. When we were in the submersible, of course, wrote things in our notebooks or in on our computers, and then transcribed all of those into an Access database. So we have very detailed information on size, shape, color, associations with other organisms, depth, location, and so on. And then if anyone is interested in more information, then we can print out a data sheet for each of these and send you a data sheet on the organism, and then you can decide if you want to work on it some more. So this is an example where we have a couple of in situ photos. This is that sponge called Liodermatium, which is a lithistid sponge, and we can take a series of close-up photos too, so that we can go back and do more taxonomic work. So I'm just going to show you now, just in the remaining few minutes, some photos of some of these deep water sponges. I just wanted to say one other thing. Over the last few years, we actually had the opportunity to move into larger space for our samples, our museum samples, and it makes it a lot easier for our colleagues to come and use the collection. And over the past few years, we've had some of my sponge colleagues, sponge experts, who've come. And when I mentioned earlier about the conservative estimate of species diversity, just in the last couple of years, we've had things that we thought were just one species of sponge have ended up being 15 different species of sponges, and that's just from one taxonomic group, from one genus, if you will. So many of the samples in our collection are not identified. They may not be identified for the sponges further than maybe an order or maybe a family. So there's a lot of opportunity there to do some classical taxonomic work as well as molecular work. So again, these are just some photos of some of the deep water sponges, just to show you a different perspective of the things that we're seeing in deep water, and some closer images of some of these areas that Gregor Eberle showed this morning. We did a lot of work on the walls, the drop-off, so around Andros, for example, and around Chub Key, where we spent a lot of time on these beautiful drop-offs. And having the ability to use the submersible, the manned submersible, was really, really a great opportunity, because these are areas where, well, number one, you wouldn't want to go in and trawl and dredge anyway. But because we had the capabilities of the submersible where we could hover, maintain our position, and go in and very precisely collect one sample at a time, or a piece of a sample at a time, gave us access to sites that we would not normally have been able to access using the traditional sampling methods of dredging and trawling, for example. So these are like very weird things that look like they're from outer space, but just different species of some of the same types of organisms that we see in shallow water. This, for example, is a sponge related to Cynocyrella that's a fairly common shallow water reef species. Same thing with this one. Lots of different things. This is my favorite ever sponge. It looks like it's a sea fan, but it's not. It's a sponge, and those veins are caused by bundles of spicules that form these siliceous spicules. Again. And again, most of this is that group of sponges that my colleague Paco Cardenas from Sweden has been working on, and last count had about 15 different species of geodias. This is a geodia sponge. Chuck, I think this was the one you were asking about earlier. Yeah. See some amazing associations here. Slit shells, lots of beautiful slit shells, usually eating the nastiest sponges that you can imagine, the ones that have the most spicules. I don't know how they deal with all of that. Beautiful glass sponges that occur deeper than about 200 meters. Again, lots of different, and originally we didn't think that these sponges, the glass sponges, because they're mostly siliceous, had a lot of bioactive compounds in them, but more recently we've been finding, when we've been using different bioassays, that they actually do. Okay, that's it. Thank you very much for your attention. I'd be happy to take questions.